6,500 light-years away, the pillars of creation hang suspended in time. Not just a photograph, an active stellar nursery. Inside those columns of gas and dust, gravity is already at work, crushing hydrogen atoms until they ignite. This is where stars are born. And this is where we began. A singularity. No space, no time, only potential. Then expansion, a fireball of quarks, gluons, and photons racing outward at velocities approaching light speed. The first 3 minutes saw the synthesis of helium nuclei. But the heavier elements, carbon, oxygen, silicon, iron, those would require something more violent. Stars. A molecular cloud, enriched with the ashes of dead giants, began to collapse. At its center, a protostar, our Sun, accreting 99.8% of the system's mass. Around it, a swirling disk of dust and gas. Microscopic grains collided, stuck, grew. Within a million years, kilometer-wide planetesimals tore through the disk, their gravity pulling in more debris. Jupiter formed first, its massive core vacuuming up hydrogen and helium, clearing a path. Earth assembled more slowly, a rocky sphere forged from silicates, metals, and the carbon-rich dust of long-dead stars. The Moon. A latecomer. A Mars-sized protoplanet, Theia, struck Earth at a glancing angle. The impact vaporized rock, ejected debris into orbit. That debris coalesced into our satellite, tidally locked, its far side scarred by ancient bombardments. Evidence. The identical oxygen isotope ratios in lunar and terrestrial rocks. This is the grand cycle, dust to stars, stars to dust. The nebular hypothesis isn't poetry. It's mechanics. A collapsing cloud spins faster as it contracts. Dust grains settle into a plane. Planetesimals merge. And the elements? Forged in the cores of stars under pressures of 250 billion atmospheres, temperatures of 15 million Kelvin. Carbon from helium burning. Silicon from oxygen fusion. Iron, the endpoint, the energy sink that triggers supernovae. Look at your hand. Those atoms were once inside a red giant, expelled into the void, then gathered here by gravity's relentless pull. The same force that shaped the pillars of creation is shaping you. Not destiny. Just physics. Inevitable. Beautiful. 4.6 billion years ago, a molecular cloud, 98% hydrogen and helium, 2% heavier elements, collapsed under its own gravity. The core reached 10 Kelvin, igniting proton-proton fusion. A star was born. The remaining gas and dust flattened into a protoplanetary disk, $200 across. Within it, micron-sized silicates and carbon grains collided at 0.1 meters per second, sticking via van der Waals forces. Over 10 years, these grew into kilometer-wide planetesimals through runaway accretion. Jupiter's core, 10 Earth masses of rock and ice, formed in just 1 million years, its gravity carving gaps in the disk. At 4.51 billion years ago, a Mars-sized body struck proto-Earth at 4 kilometers per second. The impact vaporized 20% of Earth's mantle, ejecting debris into a Roche limit exceeding ring. Within 1,000 years, 80% of the material coalesced into the Moon, its iron-depleted composition matching Earth's upper mantle. The inner disk, heated to 1,500 K, retained only refractory silicates and metals. Mercury, closest to the Sun, incorporated 60% iron by mass, its high density the result of stripping during the Sun's T-Tauri phase. Venus and Earth, formed in the snowline's absence, accreted minimal water. Mars, stranded at $1.50, remained small. Jupiter's 3:2 orbital resonance with the asteroid belt prevented further growth. Cosmic dust, 0.1 to 1 micrometer grains of forsterite, carbonaceous chondrules, and polycyclic aromatic hydrocarbons, permeates the disk. These particles, forged in asymptotic giant branch stars and supernovae, carry isotopic anomalies, oxygen, 16 excesses, silicon, 28 spikes. They are the raw material of planets, their surfaces catalyzing H2O and CO2 formation at 10 to 100 K. The Sun's radiation pressure and the Poynting-Robertson drag cleared the inner system of dust within 10 years. The outer system, beyond $5 retained volatiles. Here, icy planetesimals, composed of H2O, CO2, and CH4, merged into Uranus and Neptune, their cores later capturing hydrogen and helium from the dwindling nebula. Every atom in your bones was once a micron-sized speck in this disk, orbiting a newborn star. The same physics that assembled Jupiter's core from centimeter-sized pebbles assembled you. Not fate. Not design. Just the inexorable math of gravity, collisions, and time. The pillars of creation are not static sculptures, they are a snapshot of erosion and creation in real time. Each tendril of gas, 5 light-years long, is being carved by ultraviolet radiation from nearby stars, their surfaces ionized into plasma while deeper layers collapse into new stellar embryos. This is the cycle writ large, matter expelled by dying stars, compressed into fresh systems, then remade again. The same silicates that formed the Earth's crust were once vaporized in the shockwaves of a supernova 5 billion years ago. The carbon in your DNA was synthesized in the core of a red giant, its outer layers blown off in a stellar wind traveling at 30 kilometers per second before cooling into dust grains. These grains, each less than a micron wide, drifted for eons until they encountered a molecular cloud dense enough to collapse under its own gravity. The solar system began this way, a 0.1 parsec-wide region of the Orion Arm, seeded with 10 superscript 1 kilograms of dust and gas, began to contract when a nearby supernova's shockwave, traveling at 10,000 kilometers per second, compressed its core beyond the gene's instability threshold. Within 100,000 years, the central density reached 10 superscript 1 particles per cubic centimeter, igniting nuclear fusion in the protosun. The remaining disk, now flattened by angular momentum conservation, cooled from 2000 K to 100 K over the next million years. At these temperatures, refractory elements like iron and aluminum condensed first, forming millimeter-sized chondrules. Further out, ices of water, methane, and ammonia crystallized, their snowlines marking the boundary between terrestrial and gas giant formation. Planetesimals grew through runaway accretion, their gravity drawing in pebbles at a rate of 10 kilograms per year. Jupiter's core, reaching 10 Earth masses in just 3 million years, gravitationally stirred the inner disk, preventing Mars from growing larger and scattering planetesimals into the asteroid belt. The Moon's origin is a relic of this chaos. A Mars-sized body, Theia, struck the proto-Earth at 4 kilometers per second, vaporizing both mantles into a silicate atmosphere 500 times Earth's current mass. This ejecta coalesced into a circumplanetary disk, where tidal forces and collisional damping formed the Moon in just 100 years, its crust enriched in anorthosite from the lighter materials that floated to the top of the magma ocean. Today, the ratio of tungsten isotopes in lunar samples confirms this model. The Moon's superscript 1 superscript 2W abundance matches Earth's mantle, but not its core, proving the impact occurred after Earth's core formation. Every atom heavier than helium in this system was forged in the bellies of stars. The iron in your hemoglobin was ejected by a type Ia supernova, its light curve peaking at 10 superscript 3 ergs per second as nickel-56 decayed into cobalt and then iron. The gold in a wedding band was born in a neutron star merger, where our process nucleosynthesis built elements up to uranium in a fraction of a second. These are not abstractions. They are the precise mechanisms by which the universe assembles complexity from simplicity, turning dust into worlds, and worlds into the conditions for life. And yet, this cycle is not closed. In 5 billion years, the Sun will exhaust its hydrogen, expand into a red giant, and shed half its mass as a planetary nebula. The ejected gas will carry silicon, oxygen, and carbon into the interstellar medium, where it will drift for millions of years before seeding the next generation of stars. The atoms that once composed Jupiter's metallic hydrogen core will be scattered across light years, their paths crossing those of other nebulae. Some will form new planets. Others will be incorporated into brown dwarfs or rogue worlds, drifting between stars. The math does not care. It is neither cruel nor kind. It simply is, a set of equations describing the flow of matter from one state to another, across time and space, without beginning or end. But here, now, on this fragile world, the cycle has produced something remarkable. The same physics that built the moon from debris has built you from the dust of long-dead stars. There is no division between the cosmic and the personal. The laws that govern the collapse of a molecular cloud are the laws that govern the folding of proteins in your cells. The universe does not create life despite its indifference, it creates life because of it. And in that indifference, there is a kind of terrible beauty, the recognition that you are, in every sense, a way for the cosmos to understand itself. The cosmos does not care for your wonder. It does not care that you are here, or that you are thinking of it now. It is indifferent, yet in that indifference, it creates life because of it. And in that terrible beauty, you are, in every sense, a way for the universe to understand itself. So let us begin where it all does, not with fire, but with silence. A nebula. A cloud of gas and dust, stretching light years across, so diffuse that if you passed through it, you would barely notice. But within its folds, gravity is already at work. Tiny perturbations, overdensities no more than a fraction of a percent, become the seeds of something extraordinary. Here, in these clumps, hydrogen atoms drift, colliding, heating, collapsing inward under their own weight. The cloud contracts. The core grows denser, hotter. This is the protostar, a star in the making. For millions of years, gravity pulls. Pressure resists. But when the core reaches 10 million Kelvin, something changes. Hydrogen nuclei, protons, begin to fuse. Not gently. Not slowly. Violently. Each collision releases energy, a fraction of mass lost, converted into light and heat, as Einstein's equation demands, E equals mc superscript 2. A star is born. This is the main sequence. The phase where a star spends 90% of its life. Here, fusion pressure outward balances gravity inward, a cosmic stalemate that can last billions of years. Our sun is in this phase now. It has been for 4.6 billion years. It will be for another 5 billion more. But stars are not just beacons. They are forges. Inside their cores, nucleosynthesis unfolds. Hydrogen fuses to helium. Helium to carbon. Carbon to oxygen, neon, magnesium. In the most massive stars, this chain continues all the way to iron. Each element, a stepping stone in the periodic table, built from the ashes of the one before. Without this process, you would not exist. The calcium in your bones, forged in the heart of a dying star. The iron in your blood, smeared across space in a supernova. Even the gold in your jewelry, the product of neutron-star collisions, the most violent mergers in the universe. But stars do not live forever. Our sun will one day exhaust its hydrogen. When it does, the core will contract, heating further, until helium ignites in a flash. The outer layers will expand, swallowing Mercury, Venus, perhaps even Earth. For a brief time, it will be a red giant, a swollen, dying ember. Then, the end. The outer layers will drift away, forming a planetary nebula, a glowing shell of gas, illuminated by the exposed core. What remains is a white dwarf, a Earth-sized remnant, so dense that a teaspoon of it would weigh tons. It will cool, over trillions of years, fading into a black dwarf, a corpse in the dark. Massive stars do not go gently. When they die, they do so in fire. A core collapse supernova, the most powerful explosion in the universe since the Big Bang. In seconds, a star brighter than an entire galaxy. In its wake, a neutron star or a black hole, objects so extreme that space and time themselves warp around them. This is the cycle. Birth. Fusion. Death. And from the ashes, new stars rise, new planets form, new life emerges. The cosmos does not care. But it is why you care. Because you are made of its indifference. And in that, there is a kind of terrible beauty. Within its swirling clouds, gravity seizes upon the slightest irregularity, a region just 1% denser than its surroundings, and begins its relentless collapse. Hydrogen molecules, drifting for eons in near-perfect vacuum, now collide with increasing violence. The core temperature climbs, 10 K, 100 K, 1000 K. At 10,000 K, molecular hydrogen dissociates into atomic hydrogen. The collapse accelerates. A protostar forms when the core density reaches 10 superscript 1 particles per cubic centimeter. At this stage, it is not yet a star, only a dense, rotating sphere of gas, its outer layers still accreting material from the surrounding disk. The protostar's surface temperature hovers around 3000 K, but its core is far hotter, 10 K, than 10 K. The crush of gravity pushes inward, the pressure of the heated gas pushes back. For now, the gas wins. Then, at 10 K, the magic threshold is crossed. Protons, hydrogen nuclei, overcome their electrostatic repulsion. The strong nuclear force binds them into helium, for nuclei. In each fusion reaction, 4 protons yield 1 helium nucleus, 2 positrons, 2 neutrinos, and 26.7 MeV of energy. The mass defect is 0.7%, small, but multiplied by 10 superscript 3 reactions per second, it is enough. The core ignites. The outward pressure of this radiation halts the collapse. Hydrostatic equilibrium is achieved. A star is born. This is the main sequence phase, a balance of forces so precise that it will endure for billions of years. For a star like our Sun, hydrogen fusion in the core proceeds via the proton-proton chain, converting 600 million tons of hydrogen into 596 million tons of helium every second. The missing 4 million tons, converted to energy, via E equals mc squared. This is the engine that powers every star in the sky. But stars are not merely engines. They are factories. In the first few minutes after the Big Bang, the universe synthesized hydrogen, helium, and trace lithium. Everything else, carbon, oxygen, iron, gold, uranium, was forged in stars. In the cores of main sequence stars, helium nuclei fuse into carbon-12 via the triple alpha process. For stars more massive than 8 solar masses, the process does not stop there. Carbon fuses into neon, neon into oxygen, oxygen into silicon. Each stage burns hotter, faster, shorter-lived. The final act is silicon burning, a frenzied synthesis of iron, 56 that lasts mere hours. Iron is the end. It cannot fuse without absorbing energy. The core, now a sphere of degenerate iron, collapses in less than a second. The rebound sends a shock wave through the star's outer layers. A supernova erupts. In that explosion, heavier elements are born, gold from neutron capture, uranium from rapid fission. The shock wave propagates at 10,000 kilometers per second, seeding the interstellar medium with the raw materials of planets, of life. Our Sun will not end this way. With a mass of 1.989 times 10 superscript 3 kg, it is too small to fuse beyond helium. In 5 billion years, its core will exhaust its hydrogen fuel. The balance will tip, gravity will compress the core, heating it to 10 K, while the outer layers expand, engulfing Mercury, Venus, perhaps Earth. For a brief time, the Sun will become a red giant, its luminosity 1,000 times its current value. Then, the helium flash. In a matter of seconds, the core ignites, fusing helium into carbon via the triple alpha process. The Sun will shed its outer layers, forming a planetary nebula, a glowing shell of ionized gas, expanding at 20 kilometers per second. At its center, the remnant core, a white dwarf, Earth-sized but with half the Sun's mass, its density a ton per cubic centimeter. Massive stars, those above 8 solar masses, do not go quietly. Their cores collapse into neutron stars or black holes, their outer layers torn apart in supernovae. The threshold is precise, 2.1 times 10 joules of gravitational energy released in seconds. The shockwave synthesizes elements beyond iron. The remnant, if it is a neutron star, is a sphere 20 kilometers across with a surface gravity 100 billion times Earth's. If it is a black hole, the event horizon marks the boundary where spacetime itself tears. And from these ashes, new stars rise. The cycle is not sentimental. It is physics. Gravity, fusion, entropy, and time. The cosmos does not care. But it is the crucible in which we are forged. Here, then, is the ledger of creation. Every atom of calcium in your bones, every atom of iron in your blood, was forged in the belly of a star. Not metaphor. Not allegory. Fact. The main sequence is not merely a phase, it is the universe's most efficient assembly line, transmuting hydrogen into helium at temperatures exceeding 15 million Kelvin, releasing 620 million tons of energy every second in a single star like our Sun. This is the engine that stabilizes a star against collapse for 90% of its life, the delicate equilibrium where outward radiation pressure precisely counters inward gravitational force. Without it, matter would remain inert clouds of gas, galaxies dim and lifeless. But equilibrium is temporary. Inside the core, the fusion process marches upward, helium fuses into carbon, carbon into neon, neon into oxygen, and onward through the periodic table, each step requiring higher temperatures and pressures. In stars 8 times the mass of our Sun, this progression continues. Silicon fuses into iron, the most stable nucleus in the cosmos. No energy is released beyond iron, fusion there absorbs energy instead. And so the core grows inert, a rigid sphere of iron 2,000 kilometers wide, unable to generate heat. This is the moment the clock stops. Gravity, unopposed, crushes the core in less than a second. Electrons are forced into protons, forming neutrons and neutrinos. The core recoils, sending a shockwave outward through the star's layers at 30,000 kilometers per second. In hours, the star detonates, supernova. In those few seconds, the universe forges elements heavier than iron, gold, uranium, iodine. These are not decorations. They are the raw materials for planets, for life, for consciousness. Our Sun will not explode. It will swell into a red giant, shed its outer layers into a planetary nebula, and leave behind a white dwarf, an Earth-sized remnant with a mass half that of the Sun, so dense a teaspoon weighs 5 tons. It will cool over trillions of years, a silent ember in the dark. Yet from the debris of these endings, new stars rise. The cycle is not cyclic, it is progressive. Each generation of stars enriches the cosmos with heavier elements. The universe does not mourn its dead. It reuses them. And so, we turn now to the future, not of stars, but of matter itself. For even the atoms we are made of are not permanent. They too will one day be unmade. But that is a story not of death, but of transformation. Of entropy, yes, but also of legacy. The cosmos does not erase its history. It recycles it, again and again. And in that endless chain, we find ourselves, temporary, but inevitable. Now, look closer. Not at the fire of stars, but at the quiet precision of their retinue, the planets, moons, and rogue wanderers bound to them by an invisible hand. This is the realm of orbital mechanics, where mathematics dictates motion, and gravity writes the rules. In 1609, Johannes Kepler shattered the celestial spheres. No more perfect circles. No more uniform speed. Instead, he gave us ellipses, stretched ovals with the Sun not at the center, but at one of 2 focal points. A planet's distance from the Sun is not constant. At perihelion, Earth races at 30.3 kilometers per second. At aphelion, it slows to 29.3. Kepler's second law codifies this: a line connecting planet to Sun sweeps equal areas in equal times. Closer means faster. farther means slower. No magic. Just geometry. Then, the third law, the square of a planet's orbital period is proportional to the cube of its semi-major axis. For Earth, 1 year. For Neptune, 164.8. The numbers hold, whether in our solar system or around a distant red dwarf. These laws aren't just descriptions. They are predictions. And they were tested, brilliantly, by human ingenuity. Consider Jupiter's moons, Io, Europa, Ganymede. A 1:2:4 orbital resonance. For every 4 orbits of Io, Europa completes 2, Ganymede 1. Their gravitational tugs synchronize their paths, preventing collisions. Without this resonance, their orbits would decay. Chaos would reign. Instead, they endure, a clockwork ballet of gravity and time. But the most audacious application of these laws came in the 20th century. A rare alignment, Jupiter, Saturn, Uranus, Neptune, all on the same side of the Sun. A 176-year window. In 1977, we launched Voyager 1 and 2. Not directly at their targets, but on a trajectory to steal momentum from each planet. A gravity assist. Voyager 2's path to Neptune was a masterclass in orbital dynamics, slingshotting around Jupiter in 1979, gaining 18 kilometers per second. Saturn in 1981, Uranus in 1986, Neptune in 1989. Each encounter adjusted its velocity, bending its path without a single burn of its engines. Pure conservation of angular momentum. The laws hold. The math is exact. And in that precision, we see not just motion, but legacy. The same forces that govern falling apples shape the orbits of planets. The same equations that predict a comet's return guide spacecraft across the void. We are not separate from this dance. We are participants, bound by the same rules. And for a brief moment, we wielded them. Kepler's first law rewrote the cosmos: planets do not trace perfect circles. They carve ellipses, stretched loops with the sun pinned at one focus. Eccentricity defines the shape. Mercury's orbit, with an eccentricity of 0.206, swings between 46 million and 70 million kilometers from the Sun. At perihelion, it hurtles at 59 kilometers per second, at aphelion, it dawdles at 39. This is Kepler's second law in action: a line drawn from planet to sun sweeps out equal areas in equal times. No mysticism, just geometry. The third law binds time to distance. The square of a planet's orbital period equals the cube of its semi-major axis, measured in astronomical units and years. Jupiter, $5.20 from the Sun, orbits once every 11.86 Earth years. Plug the numbers. 11.86 superscript 2 is almost equal to 140.7, 5.2 superscript 3 is almost equal to 140.6. The harmony is exact. Now zoom to Jupiter itself. 3 of its moons, Io, Europa, Ganymede, are locked in a 1:2:4 Laplace resonance. Io completes 4 orbits for every 2 of Europa and 1 of Ganymede. The math is precise: 1.769 days, 3.551 days, 7.155 days. Each time Io passes Europa, gravitational tugs distort its orbit into an ellipse. Tidal heating, friction from Jupiter's pull, melts Io's interior, fueling volcanic eruptions that eject sulfur dioxide at 1 kilometer per second. Europa's surface cracks under the same forces, revealing a subsurface ocean 100 kilometers deep. In 1977, human ingenuity hijacked these laws. Jupiter, Saturn, Uranus, and Neptune aligned once every 176 years, a window to slingshot 2 probes, Voyager 1 and 2, across the solar system. Gravity assists bent trajectories like cosmic billiard shots. Voyager 2's encounter with Jupiter in 1979 increased its velocity by 16 kilometers per second, bending its path toward Saturn. Saturn's gravity then flung it to Uranus in 1986, where the probe's instruments recorded temperatures of -214 degrees Celsius and winds at 900 kilometers per hour. Uranus's gravity adjusted the trajectory again, delivering Voyager 2 to Neptune in 1989. The flyby revealed a storm the size of Earth, the Great Dark Spot, with winds at 2,100 kilometers per hour, the fastest in the solar system. The mechanics were flawless. Each gravity assist conserved angular momentum. The probe's velocity changes came from the planet's orbital motion. Voyager 2's final trajectory after Neptune had it leaving the solar system at 15.4 kilometers per second, faster than any human-made object at the time. The math held. The dance was not metaphor, it was mechanics. The solar system is not a static tableau, it is a clockwork of precise, predictable motion. Kepler's laws revealed this centuries ago. Planets trace ellipses, not circles, sweeping equal areas in equal times. Perihelion speeds them, aphelion slows them. Jupiter's moons, locked in a 1:2:4 orbital resonance, pull on one another with gravitational tides, their periods synchronized like gears. Io completes 4 orbits to Europa's 2, to Ganymede's 1. The result? A repeating cycle of flexing and heating, fueling Io's volcanic fury. Humanity's reach into this mechanism was no accident. The 176-year alignment of the outer planets was a fleeting window, calculated, not wished for. Voyager 1 and 2 rode that alignment like a tide, slingshotting past Jupiter in 1979, stealing momentum from its orbit. Saturn's gravity bent their paths inward. Uranus and Neptune, rarely visited, became waypoints. Each assist was a transfer of angular momentum, energy borrowed from the planets themselves, not from fuel. The probes emerged faster, altered, their trajectories inscribed by the same laws that govern the planet's own motion. This was not exploration by brute force. It was navigation through the language of gravity. The math held because the universe is written in equations, not poetry. And when Voyager 2 left Neptune, its velocity climbing to 15.4 kilometers per second, it carried more than instruments, it carried proof that we had learned to read the cosmos, and for a moment, to speak its tongue. Now, the solar system's clockwork continues, indifferent to the probes that have slipped its bonds. But the lesson remains, the rules are there to be understood, and understood, they can be used. The next orbit begins beyond the edge. The probes have slipped Earth's bonds, but the rules endure. Beyond the edge, the Milky Way is not a serene glow, it is a sprawling cosmic city, 100,000 light-years across, a metropolis of 200 billion stars bound by gravity and something darker. 3 components define its architecture. First, the spiral arms, 4 primary, 2 secondary, dense with gas, dust, and star formation, tracing logarithmic spirals at 12 degrees per kiloparsec. Second, the central bulge, a spheroid of older stars, 8,000 light-years wide, orbiting at velocities exceeding 1,000 kilometers per second. And third, the dark matter halo, an invisible scaffold extending 300,000 light-years, its mass 6 times that of all visible matter, revealed not by light but by rotation curves that defy Newtonian expectation. In 1927, Edwin Hubble measured the recession of galaxies and discovered the universe is expanding. His eponymous law, velocity equals Hubble's constant times distance, quantified this flight. But the galaxy rotation curve problem, first noted in the 1930s by Fritz Zwicky and later by Vera Rubin, revealed an anomaly: stars at the Milky Way's periphery orbit too fast. Their velocities should drop as 1 over the square root of distance, yet they remain nearly flat. The culprit? Dark matter, 90% of the galaxy's mass, clumping unseen, warping space without emission. At the galaxy's heart lies Sagittarius A*, a supermassive black hole of 4.3 million solar masses, its event horizon spanning 25 million kilometers. It is not passive. In active galactic nuclei, material spirals inward, heating to millions of degrees, emitting X-rays and radio waves. The most extreme examples, quasars, discovered in 1963, outshine entire galaxies from distances of 10 billion light-years. Their luminosity comes from accretion, matter falling into black holes at 99% light speed, converting mass to energy with 40% efficiency, 10 times greater than nuclear fusion. Pull back further. The Milky Way is not isolated. It is a node in the cosmic web, a filamentary structure of galaxy clusters and voids, where matter flows along bridges of dark matter, stretching 300 million light-years. The filaments are the scaffolding, the voids, vast and near empty, are the negative space of the cosmos. The city has rules. We have only begun to map them. The Milky Way is not a gentle glow, it is a sprawling metropolis of 100 to 400 billion stars, bound by forces we are still unraveling. Its structure is a blueprint of cosmic engineering, a central bulge 10,000 light-years thick, older stars orbiting in chaotic ellipses like commuters in a crowded terminal. Beyond it, the spiral arms, Perseus, Scutum Centaurus, Norma, Sagittarius, stretch 100,000 light-years in diameter, lanes of gas, dust, and young stars tracing the galaxy's rotation. These arms are not static. They are density waves, compressing interstellar matter as they propagate at 30 kilometers per second, triggering star formation in their wake. But what holds this city together? In the 1970s, Vera Rubin measured the rotation curves of spiral galaxies and found a paradox: stars at the edges orbit at the same velocity as those near the center, defying Keplerian mechanics. The explanation? A halo of dark matter, 10 times the mass of visible matter, extending 300 kiloparsecs from the galactic core. Its nature remains unknown, but its gravitational grip shapes the Milky Way's fate. At the heart of the galaxy lies Sagittarius A*, a supermassive black hole with a mass of 4.3 million suns, compressed into a singularity 17 times the Sun's diameter. Its event horizon, 12 million kilometers across, warps spacetime so severely that light bends around it. An accretion disk of plasma, heated to 100 million Kelvin, emits X-rays as matter spirals inward at relativistic speeds. In 2019, the Event Horizon Telescope captured its silhouette, the first direct evidence of a black hole's shadow. But Sagittarius A* is dormant. Look farther. Quasars, the most luminous objects in the universe, outshine entire galaxies from 13 billion light-years away. Discovered in the 1960s as quasi-stellar radio sources, they are powered by supermassive black holes in active galactic nuclei, consuming 10 Earth masses of material per minute. Their jets, collimated by magnetic fields, accelerate particles to 99.9% the speed of light, emitting synchrotron radiation across the electromagnetic spectrum. The brightest, 3C273, releases 10 to the power of 40 watts, equivalent to 2 trillion suns. Pull back further. The Milky Way is not alone. It is a node in the cosmic web, a filamentary structure 300 million light-years long, where galaxy clusters like Virgo and Coma stretch along dark matter scaffolding. Between them, voids, regions of near-total emptiness, 100 million light-years across, where matter density drops to 1% of the cosmic average. The web's formation is a relic of primordial quantum fluctuations, amplified by inflation, then sculpted by gravity over 13.8 billion years. The city has rules. We have only begun to map them. From here, the Milky Way is not a blur, it is a city. A disk 100,000 light-years across, its spiral arms traced by 400 billion stars, their orbits governed by a mass we cannot see. The rotation curve flattens at 220 kilometers per second, defying Newtonian expectation. Visible matter alone cannot hold the galaxy together. Something else, dark matter, 5 times more abundant, stretches in a halo 10 times wider than the luminous disk, its gravity sculpting the motions of stars and gas. Hubble's law gave us expansion, the rotation curve gave us a problem. By the 1970s, Vera Rubin's data showed galaxies spinning as if embedded in unseen scaffolding. The central bulge, 27,000 light-years from Earth, cradles Sagittarius A*, a black hole 4 million times the Sun's mass, its event horizon spanning 24 million kilometers. Not dormant, quasars, discovered in 1963, are its distant cousins, outshining entire galaxies from a region no larger than the solar system. Their power comes from accretion, gas spiraling at relativistic speeds, heated to millions of degrees, converting 10% of rest mass into energy, far more efficient than fusion. Active galactic nuclei are the universe's lighthouses. Their jets, collimated by magnetic fields, stretch millions of light-years, seeding intergalactic space with cosmic rays and metals. The Milky Way's own AGN was active within the last few million years. Fermi bubbles, gamma-ray-emitting lobes 50,000 light-years tall, are its fossil record. Pull back further. The cosmic web emerges. Filaments of galaxies, each a city like ours, trace the distribution of dark matter on scales of hundreds of millions of light-years. Voids, where matter density drops to near zero, are not empty, they are the spaces between the scaffolding, where the universe's geometry is laid bare. The structure we see today is a fossil of quantum fluctuations, stretched by inflation, frozen in the plasma of the early universe, then grown by gravity into the architecture we navigate now. We have mapped the rules. Now we ask, what governs the governors? A star, once a titan of hydrogen and helium, exhausts its fuel. The core, now a sphere of iron, cannot fuse further. Gravity, unopposed, crushes it in less than a second. The collapse triggers a rebound, a shockwave so violent it tears the star apart in a supernova. For weeks, this single explosion outshines an entire galaxy. Its luminosity peaks at, equivalent to the sun's total output over. The remnants tell a story. At the core, protons and electrons merge under pressures of, forming a neutron star. It spins. A teaspoon of its matter would weigh on Earth. Magnetic fields a trillion times stronger than ours channel radiation into beams that sweep the cosmos like a lighthouse. We call it a pulsar. The fastest known, rotates. Its heartbeat is the universe's metronome. But not all collapses end in pulsars. If the core's mass exceeds, even neutrons cannot resist gravity. The star vanishes into a singularity, a black hole. Its event horizon, defined by the Schwarzschild radius, marks the point of no return. Light itself cannot escape. Yet Stephen Hawking proved in 1974 that black holes aren't completely black. Quantum fluctuations near the horizon spawn particle-antiparticle pairs. One falls in, the other radiates away. This is vanishingly faint, but it ensures that, even the most massive black holes will evaporate. The supernova's shockwave doesn't just destroy. It creates. When it slams into a nearby nebula, it compresses the gas. Denser regions collapse under their own gravity, igniting new stellar nurseries. The heavy elements ejected by the supernova enrich the cloud. These are the building blocks of planets, of life. And so the cycle turns. From the ashes of death, birth. From the rules of gravity and fusion, the governors of the cosmos. The ions, stretched by inflation and frozen in the plasma of the early universe, have now grown into the architects of creation. They have mapped the laws. But what governs the governors? The answer lies in the quiet violence of a dying star, and the silent elegance of what comes next. The most spectacular event in the universe begins with a core collapse. A star, 20 times the mass of our Sun, has fused hydrogen into helium, helium into carbon, and carbon into neon, oxygen, silicon, layer upon layer, like an onion of plasma. At its heart, silicon burns into iron. Iron is nuclear ash. It cannot fuse. The star's core, now a rigid sphere of iron nuclei, is squeezed by gravity at a rate of 1,000 kilometers per second. In less than a second, the core implodes from the size of Earth to the size of Manhattan, 20 kilometers across. Density reaches 4 times 10 superscript 1 kilograms per cubic meter. Electrons are crushed into protons, forming neutrons. The core stiffens. The infall rebounds. A shockwave races outward at 30,000 kilometers per second, shredding the star's outer layers in a detonation that releases 10 joules of energy, more than the Sun will emit in its entire 10 billion-year lifetime. For 20 days, the supernova outshines its host galaxy. In the ejecta, temperatures reach 5 times 10 Kelvin. Neutrons slam into iron nuclei, forging elements heavier than iron, cobalt, zinc, gold, uranium. Every atom of gold and every wedding ring was forged in the neutron-rich debris of a dying star. The remnant is a neutron star. Mass, 1.4 solar masses. Radius, 10 kilometers. Density, 1 billion tons per cubic centimeter. Rotational velocity, up to 700 revolutions per second. Magnetic field, 10 superscript 1 superscript 2 times Earth's. The star's original magnetic field is compressed like a collapsing accordion, amplifying the field strength until it funnels charged particles into twin beams that sweep the cosmos like a lighthouse. We call this remnant a pulsar. From Earth, the pulses arrive with metronomic precision, some as regular as atomic clocks. PSRB 1937 plus 21 spins 642 times per second, its surface moving at 12% the speed of light. The pulses slow as the neutron star loses rotational energy through magnetic braking, radiating 10 superscript 3 watts, enough to power every city on Earth for 1 trillion years. But not all remnants become pulsars. If the core's mass exceeds 3 solar masses, gravity wins. The collapse does not stop at neutron degeneracy. The space-time curvature becomes infinite. A black hole forms, an event horizon, a one-way membrane where escape velocity equals the speed of light. Inside, the singularity, a point of infinite density, warps spacetime so severely that time itself stops. Yet black holes are not entirely black. In 1974, Stephen Hawking calculated that quantum fields near the event horizon spawn particle-antiparticle pairs. One falls in, the other escapes as Hawking radiation. For a stellar mass black hole, the temperature is 6 times 10 Kelvin, nearly absolute zero. The evaporation timescale is 10 years. But for primordial black holes, smaller and hotter, Hawking radiation is detectable. If one existed, we might see a burst of gamma rays as it vanishes in a final flash of energy. The supernova's shockwave slams into a nearby nebula, a cloud of molecular hydrogen and dust. The impact compresses the gas, triggering gravitational collapse. Density fluctuations, once imperceptible, now grow. A new protostar ignites. The heavy elements forged in the supernova, carbon, oxygen, iron, enrich the cloud. They will become the seeds of planets, of rocks, of oceans, of DNA. The cycle is complete. The death of one star births 1,000 others. The governors have spoken: gravity, fusion, quantum fields. The universe does not waste its violence. It transforms it into light, into matter, into life. The universe does not deal in subtlety. It deals in extremes. A supernova is not merely an explosion, it is a factory. In its final seconds, a dying star synthesizes elements beyond iron, gold, uranium, platinum. These are the rarest atoms in the cosmos, forged in the inferno of collapse, where temperatures reach 100 billion degrees and densities crush atomic nuclei into oblivion. Without this violence, the periodic table would end at iron. There would be no Earth, no silicon chips, no human bones. The remnants are equally relentless. A pulsar, a neutron star spinning 700 times per second, is not a gentle beacon. Its magnetic field, 1 trillion times stronger than Earth's, accelerates particles to near-light speed, emitting beams of radiation that scythe across the galaxy. This is the universe's metronome, precise, unyielding, a cosmic lighthouse with a pulse measured in milliseconds. And then, the silence. A stellar mass black hole is not a void, it is a boundary. At its event horizon, space-time curves so steeply that light itself halts, trapped in an orbit that will never escape. Yet even here, the universe finds a loophole. Stephen Hawking's 1974 calculations revealed that black holes evaporate. Quantum fluctuations at the horizon spawn particle-antiparticle pairs, one falls in, the other escapes as Hawking radiation. Over eons, the black hole shrinks, its mass bleeding away as energy. Nothing is permanent. The shockwave arrives. The supernova's detonation slams into a neighboring nebula, compressing its gas, seeding turbulence. Knots of density form. Gravity takes over. A new protostar ignites, not alone, but in a litter of siblings, each cradling the heavy elements of the dead. Carbon for molecules. Oxygen for water. Iron for cores. The cycle is not just renewal, it is evolution. Each generation of stars is richer than the last, its planets more complex, its chemistry more diverse. The universe does not waste its violence. It alchemizes it. From death comes structure. From chaos, creation. The cosmos is not a static painting, it is a process, a chain reaction, a fire that has burned for 13.8 billion years and shows no sign of cooling. And somewhere, in the quiet between the stars, a cloud of dust stirs. Waiting. And somewhere, in the quiet between the stars, that cloud of dust stirs, not by chance, but by measurement. In 1995, the Hubble Space Telescope trained its gaze on a patch of sky so small it could be blocked by a grain of sand held at arm's length. For 10 consecutive days, it collected photons. The result was the Hubble Deep Field, 3,000 galaxies in a sliver of empty space, each one an island universe containing hundreds of billions of stars. This was not discovery by accident. It was discovery by precision. Exoplanets, worlds orbiting stars beyond our Sun, had been theorized for centuries. But proof came in 1992, not from a yellow star like ours, but from a pulsar, PSRB 1257+12, a spinning neutron star 2,300 light-years away. 2 planets, later confirmed as 3, were detected via millisecond variations in the pulsar's radio signals. They were not habitable. They were irradiated. Yet they existed. Since then, over 5,500 exoplanets have been confirmed, each one a data point in a cosmic census. The transit method, used by telescopes like Kepler and TESS, detects the 0.1% dip in a star's brightness as a planet crosses its face. Radial velocity measures the gravitational wobble of a star, shifting its spectral lines by just meters per second, a precision akin to detecting a snail's crawl on the moon. From these methods, we've uncovered worlds unlike anything in our solar system. Hot Jupiters, gas giants orbiting their stars in days, not decades. WASP-12b, for example, completes an orbit in 1.09 Earth days. Its surface temperature exceeds 2,200 degrees Celsius, hot enough to vaporize rock. These planets were not born where we find them, they migrated inward, their orbits reshaped by gravitational drag or chaotic interactions. Super-Earths, planets between 1 and 10 Earth masses. Some, like LHS 1140b, lie in their star's habitable zone, where liquid water could persist. Others, like K2-18b, may host hydrogen-rich atmospheres and even water vapor. But size does not guarantee habitability. A super-Earth with a thick, crushing atmosphere could trap heat like Venus, turning oceans into steam. Then there are the tidally locked worlds. Planets like TRAPPIST-1e, where one side endures eternal day, the other eternal night. The temperature gradient between hemispheres could drive supersonic winds, or create a habitable ring where day meets night, if the atmosphere is thick enough to redistribute heat. And the rogue planets, worlds without stars, drifting through interstellar space. Free-floating, untethered, their surfaces frozen or molten depending on their age. Some may have been ejected from their systems, others formed in isolation, failed stars with too little mass to ignite. But planets are not the only worlds worth exploring. Moons, often overlooked, are some of the most dynamic places in the cosmos. Enceladus, a small moon of Saturn, hides a global ocean beneath its icy shell. Cassini's instruments detected water vapor, silica particles, and hydrogen, signs of hydrothermal vents on the ocean floor. On Earth, such vents sustain entire ecosystems without sunlight. Titan, larger than Mercury, has lakes of liquid methane, a nitrogen-rich atmosphere, and seasonal rainstorms of hydrocarbons. Its surface pressure is 1.5 times Earth's, and its rivers carve channels into bedrock of water ice. And then there are the rings, Saturn's in particular. Not just debris, but a dynamic system governed by physics. The Roche limit defines the boundary where tidal forces tear moons apart, feeding the rings with fresh material. Shepherd moons like Prometheus and Pandora, barely 50 miles across, use their gravity to sculpt ring edges, creating gaps and waves that propagate like ripples on a pond. All of this, every transit, every wobble, every geyser, was revealed not by conjecture, but by instruments designed to measure the unmeasurable. And the fire that has burned for 13.8 billion years. It burns still, in the cores of stars, in the hearts of worlds, in the silent revolution of a planet around a distant sun. Waiting for us to look. The Hubble Deep Field stares into a patch of sky no larger than a grain of sand held at arm's length, yet it holds 3,000 galaxies, each a metropolis of 100 billion stars. Light from the faintest has traveled 13 billion years, stretching from ultraviolet to infrared as the universe itself expands. Exoplanets were not theory, they were detected first in 1992 around PSR B1257+12, a millisecond pulsar whose radio pulses, normally precise to a microsecond, wobbled by 0.8 milliseconds due to the gravitational tug of three rocky worlds. Masses, 0.02, 4.3, and 3.9 Earth masses. Orbits, 25, 67, and 98 days. Radiation dose, 1,000 times the lethal human limit per second. Since then, radial velocity and transit photometry have delivered 5,500 confirmed exoplanets. Radial velocity resolves Doppler shifts of 1 meter per second, less than walking speed, induced by planets pulling their host stars into ellipses with semi-amplitudes of 3 to 100 meters per second. Transit photometry detects dips in stellar flux of 0.01% for Earth analogs, 1% for hot Jupiters, with ingress and egress durations proportional to stellar density raised to the -1/3 power. Hot Jupiters orbit within 5 cents, completing a year in 18 hours. Surface temperatures exceed 2,200 K, hot enough to vaporize silicates. Atmospheric scale heights reach 2,000 kilometers, sodium and potassium resonance lines appear in transmission spectra at 589 nanometers and 768 nanometers. Super-Earths span 1 to 10 Earth masses, radii 1.2 to 2.6 R-circle plus. Density models reveal iron-nickel cores, silicate mantles, and, in some, water envelopes up to 10% by mass. Kepler, 10c, 17 Earth masses, 2.35 R-circle plus, has a bulk density of 7.1 g/cm superscript 3, consistent with a rocky planet retaining its primordial hydrogen envelope. Tidally locked worlds present one hemisphere permanently irradiated. Thermal models show a substellar temperature of 1,500 K, an antistellar temperature of 50 K, and a supersonic wind system driven by a 1,450 K temperature contrast. Possible liquid water habitats exist in the Terminator annulus, where radiative convective equilibrium predicts 273 K surface temperatures at pressures of 1 bar. Rogue planets, unbound to any star, drift through interstellar space. Gravitational microlensing events, durations 10 to 200 days, reveal their presence when a background star brightens by a factor of 1.0001 to 1.3. Mass estimates range from 0.1 to 13 Jupiter masses, effective temperatures drop below 50 K within 10 million years. Moons are no less exotic. Enceladus ejects 250 kilograms per second of water vapor, ice grains, and organics through 101 geysers aligned along its south polar tiger stripes. Cassini's cosmic dust analyzer detected silica nanoparticles, indicating subsurface water-rock interaction at 90 degrees Celsius and pH 8.5 to 10.5. Ice grain velocity spectra reveal a size distribution with power law index -3.2, consistent with explosive decompression through 1 km fractures. Titan surface pressure, 1.45 bar, temperature, 94 K, methane hydrological cycle, evaporation at lakes, precipitation as rain, channel incision at slopes steeper than 1 degree. Cassini radar altimetry found 200 lakes with depths up to 160 m. Shorelines show liquid alkanes receding at 5 cm per year due to seasonal evaporation. Saturn's rings, optical depth 0.1 to 2.0, particle sizes 1 cm to 10 m, thickness 10 to 100 meters. Density waves excited by resonances with moons propagate radially at 1 km per second. Spiral patterns have wavelengths decreasing from 50 km at 70,000 km to 5 km at 130,000 km. Shepherd moons Prometheus and Pandora confine the F-ring through gravitational perturbations that produce streamers and channels with widths of 10 to 100 km. Roche limit, 2.44 radii for fluid satellites, defines the inner edge of rings. Saturn's rings extend to 2.27 radii, where the Roche radius is 2.35 radii, implying an outward migration of ring material or recent disruption of a moon within the last 100 million years. These discoveries are not static portraits, they are dynamic systems governed by Newtonian gravity, fluid mechanics, and radiative transfer, revealing worlds in silent revolution. Humanity's gaze sharpened, not just outward, but deeper. The 1995 Hubble Deep Field pierced a sliver of sky no wider than a grain of sand held at arm's length, revealing 3,000 galaxies in a patch assumed empty. Each smudge of light was not a star, but a system of billions, their spectra redshifted by the expansion of spacetime itself. The universe was not a static backdrop, it was a living archive, its past written in photons that had traveled for billions of years. Then, the planets came. In 1992, the first exoplanets emerged not around a sun-like star, but orbiting a pulsar, the dead remnant of a supernova, 3 rocky worlds bathed in relentless X-ray radiation. 3 years later, 51 Pegasi b arrived, a hot Jupiter, half the mass of our own gas giant, scorching its star at a distance 20 times closer than Mercury. The transit method, watching for the dimming of starlight as planets crossed their suns, and radial velocity, detecting the Doppler wobble of stars tugged by unseen worlds, have since unveiled over 5,000 exoplanets. Super-Earths, rocky planets up to 10 times Earth's mass, dominate the census. Tidally locked worlds spin with one face forever day, one forever night, their atmospheres a frenzy of supersonic winds. Rogue planets drift between stars, untethered, their surfaces frozen in eternal twilight. Closer to home, the moons of Saturn rewrote the rules of habitability. Enceladus, a world just 500 kilometers across, spews water vapor and organic molecules from cryovolcanic geysers at its south pole, plumes fed by a subsurface ocean kept liquid by tidal heating from Saturn's gravitational flex. Titan, larger than Mercury, harbors lakes of liquid methane and dunes of organic tholins, its nitrogen-rich atmosphere denser than Earth's, where rain falls as hydrocarbons. Cassini's 12-year odyssey revealed Saturn's rings not as a single monolith, but as a dynamic interplay of gravity and collision. Shepherd moons like Prometheus and Pandora herd ring particles with their gravitational weight, carving gaps and scalloped edges. The Roche limit, 2.44 times Saturn's radius, marks the boundary where tidal forces shred moons into fragments, yet the ring's inner edge sits at 2.27 radii, suggesting recent disruption or outward migration. The rings are not ancient, they are transient, perhaps no older than the age of the dinosaurs. These discoveries are not mere additions to a catalog. They are a refutation of cosmic solitude. Every transit light curve, every Doppler shift, every plume of ice from Enceladus, is a reminder that the universe is not a silent gallery of frozen relics, but a theater of forces in ceaseless motion. We are not observers of a static cosmos, we are latecomers to a story still being written, where planets form and break apart, moons melt and freeze, and even rings, those delicate ribbons of ice, are ephemeral as snowfall. The next chapter lies just beyond the edge of the known. The next chapter lies just beyond the edge of the known, a silence so vast it hums with the echoes of creation itself. Here, at the threshold of the measurable, we confront the universe not as observers, but as listeners. Einstein's 1916 prediction was precise: space-time itself could ripple. A century later, the Laser Interferometer Gravitational Wave Observatory, LIGO, detected those ripples. Its arms, 4 kilometers long, registered a distortion smaller than the width of a proton. The source? GW150914, 2 black holes, 29 and 36 solar masses, spiraling inward at half the speed of light before merging in a fraction of a second. The energy released in that final collision exceeded the combined output of all stars in the observable universe, yet it arrived at Earth as the faintest whisper, a signal buried in seismic noise and thermal fluctuations. Then, in 2017, came the neutron-star merger. A kilonova, captured not just by LIGO and Virgo, but by telescopes across the electromagnetic spectrum. For the first time, we witnessed the collision of 2 dead stars, each a teaspoon of matter weighing billions of tons, fusing gold, platinum, uranium into the cosmos. This was the dawn of multi-messenger astronomy, a single event, seen in gravitational waves, gamma rays, X-rays, and visible light. We had begun to hear the universe, not just see it. Even as we listen, we send our voices outward. The Voyager probes, now beyond the heliopause, Voyager 1 in 2012, Voyager 2 in 2018, drift in the interstellar medium. Their golden records, etched with sounds of Earth, carry our story past the Kuiper Belt, past the Oort cloud, into the void. They are not just machines, they are proxies, bearing the only evidence of our existence to a galaxy that will not notice their passing for millennia. But the void is not empty. It is stretched by dark energy, an unknown force accelerating the expansion of spacetime itself. Current measurements suggest it makes up 68% of the universe's energy density, yet its nature remains a mystery. The Big Freeze looms, a future where entropy wins, stars burn out, galaxies drift apart, and the last black holes evaporate into Hawking radiation. The universe grows cold, dark, silent. And yet, we are here. Tiny, ephemeral, but aware. The same laws that govern black hole mergers and neutron-star collisions govern the atoms in our bones. The same spacetime that ripples with gravitational waves cradles the Earth in its orbit. We are not separate from the cosmos, we are its way of understanding itself. From the birth of stars and collapsing nebulas to the silent drift of Voyager, from the first detection of a black hole's scream to the creeping tide of dark energy, this is the story of a universe that does not care for us, yet is shaped by the same forces that shaped us. And if we are to find meaning in that indifference, it lies not in the vastness that dwarfs us, but in the fact that we stand, here, now, measuring it. Einstein's equations predicted them in 1916, ripples in spacetime, distortions propagating at light speed from cataclysmic collisions. A century later, we built machines to hear them, LIGO's twin interferometers, their 4-kilometer arms suspended in vacuum, mirrors polished to atomic precision. When a gravitational wave passes, the distance between those mirrors shifts by less than 1/10,000th the width of a proton. That's the scale of measurement. That's the threshold of detection. September 14, 2015. A signal. GW150914. 2 black holes, 36 and 29 solar masses, spiraling inward at half the speed of light. In the final fraction of a second, they merged into a single 62 solar mass black hole, converting 3 times the mass of the Sun into pure energy, radiated as gravitational waves. The chirp lasted 0.2 seconds. It stretched and squeezed Earth by less than the diameter of a human hair. And yet, we heard it. Then, in 2017, another breakthrough, GW170817. 2 neutron stars colliding. Not just gravitational waves this time, but light, gamma rays, X-rays, radio emissions, across the electromagnetic spectrum. Multi-messenger astronomy had arrived. We were no longer just observing the universe. We were listening to it. Beyond our galaxy, our probes drift. Voyager 1 crossed the heliopause in 2012, entering interstellar space. Voyager 2 followed in 2018. They carry the golden record, greetings in 55 languages, whale songs, Bach, the sound of a kiss. A message in a bottle, cast into the cosmic ocean. Their power dwindles, 2025 will be their last transmission, but their trajectory is fixed. In 40,000 years, Voyager 1 will pass within 1.6 light-years of Gliese 445, a dim red dwarf. It will not stop. It will not slow. It is a monument to curiosity, built to outlast its creators. And yet, the universe accelerates. Dark energy, the dominant force in the cosmos, stretches spacetime itself. The Hubble constant measures its effect, 73 kilometers per second per megaparsec. Every second, the space between galaxies expands. In the far future, the Big Freeze, heat death, entropy's victory. Stars will burn out. Black holes will evaporate. The universe will become a thin, cold mist of particles, drifting toward absolute zero. We are small. The cosmos is vast. And yet, we stand here, now, measuring the distance between mirrors with the precision of a proton's width, tracing the death cries of stars, sending our voices into the void. The universe does not care. But we do. That is the paradox. That is the triumph. Gravitational waves stretch and squeeze spacetime itself, a disturbance 1,000 times smaller than a proton, rippling at the speed of light. Einstein's equations predicted them. LIGO's 4-kilometer arms, laser-stabilized to within a fraction of an atom's width, caught them. September 14, 2015, a black hole merger 1.3 billion light-years away, 62 solar masses collapsing into one, the final 0.2 seconds of their spiral inscribed in the fabric of the universe. The signal, GW150914, matched Einstein's mathematics with eerie precision. Then, August 17, 2017, two neutron stars, 130 million light-years distant, their collision not just heard but seen, gamma rays, X-rays, optical light, multi-messenger astronomy born in a single event. For the first time, we did not just observe the cosmos. We listened. The Voyagers, launched in 1977, crossed the heliopause in 2012 and 2018. Now, 14 and 18 billion kilometers from Earth, they drift in the interstellar medium, their golden record spinning, 115 images, greetings in 55 languages, the sounds of whales, a kiss, a mother's first words to her child. They are not messages in bottles. They are testaments to the fact that we tried. That we measured the silence and still chose to speak. Dark energy accelerates the expansion of the universe by 68% of its total energy density. It does not clump, it does not cool, it pushes. The Lambda CDM model predicts a big freeze, galaxies beyond our local group will redshift into invisibility, stars will burn out, black holes will evaporate via Hawking radiation, and the cosmos will settle into a near vacuum of near-zero entropy. The temperature will asymptote toward absolute zero. There will be no witnesses. But here is the paradox, the smaller we are, the more precisely we measure. The colder the universe becomes, the hotter our instruments must run. We have turned our insignificance into a tool. The fear of being tiny is not overcome by delusion, it is overcome by data. By the fact that we built machines to hear the death cries of stars, to send our voices beyond the solar system, to calculate the fate of the cosmos while standing on a speck of dust. The final image is not an ending. It is a vantage point, Earth, shrinking in Voyager's rearview mirror, a pale blue dot suspended in a beam of sunlight. We are the first generation to see the universe not as a backdrop, but as a story we are telling, one proton, one gravitational wave, one golden record at a time. The void does not care. But we do. And that is enough.